Namaskar. Today we will see an overview of remote sensing technology. Remote sensing is technique of acquiring information about an object by a recording device that is not in physical contact with the object, and it is done by measuring a portion of reflected or emitted electromagnetic radiation from Earth's surface. The definition that has been adopted by United Nations in 1999 says that remote sensing is the sensing of Earth's surface from space by making use of properties of electromagnetic waves emitted or reflected by the sensed objects, and it is done for the purpose of improving natural resource management, land use and protection of environment. There are different stages in remote sensing. The remote sensing process, the prerequisite is that we have a energy source or a source illuminating my target. So that is the first step of remote sensing process. The energy source can be passive, that means the natural energy from sun can be used for recording, or the sensor can have its own source of energy, which is called as active remote sensing. The second step in remote sensing process is the energy from the energy source, let's say assume sun. So the energy travels from its source to the target, which is our earth, and it interacts with atmosphere in between. The energy after interaction from the earth's surface will be recorded by the sensor. Again it travels to the sensor via the atmosphere. Certain processes take place during the transfer via atmosphere. The third step in remote sensing process is the interaction of this energy with our target, which is basically Earth's surface. There are number of changes which happen in both the radiation and the target based upon their properties. The fourth step in remote sensing process is recording of this energy by a sensor which is not in contact with the object, but in fact it is on board a satellite which is orbiting the earth. The fifth step in remote sensing process is whenever this satellite comes in contact with the ground station, the energy recorded by the sensor will be transmitted and it will be received by the ground station, from where it will be sent to the users either in a hard copy imagery or more commonly nowadays digital imageries. The next step would be the interpretation and analysis of these images by experts in the field or trained people in the field, both visually or digitally, to extract meaningful information about the target from which the energy has been recorded. The last step would always be utilizing this information interpreted for useful application for decision making purposes. Now, why we are going into remote sensing, the advantages of remote sensing is the large regions can be observed over time. As we can see, if we stand at the ground, we have a limited field of view. As we go higher and higher, we have a synoptic view of the area. So large regions can be observed. We can have a global and periodic coverage of the Earth's surface, repeated coverage. Then sensors can measure energy at the wavelengths beyond the range of the human vision, and their information is being recorded in real time. The process is repeatable and more cost effective than manual methods of data collection. Now, the first source of energy which we discussed. So the energy source is electromagnetic radiation. Whatever is recorded is electromagnetic radiation, and electromagnetic waves basically are characterized by their wavelengths and frequency. If we arrange electromagnetic waves according to either wavelength or frequency, we call it electromagnetic spectrum. And there are many regions of this electromagnetic spectrum which are useful in remote sensing. The regions which are mostly used in remote sensing are optical remote sensing region from 0.4 micrometer to 3 micrometers, thermal infrared remote sensing from 3 micrometers to 14 micrometers, and microwave remote sensing 1 millimeters to 1 meter. The advantage of having this longer wavelengths is that they can penetrate through haze, light rains, snow, cloud and smoke. And it also has the active microwave. That means whenever the sensor is sending its own source of energy, it also has the night vision capability, and it is not affected by the atmosphere. It can penetrate the canopy. Now energy, the next step is interaction of this electromagnetic radiation with earth surface, because it is the energy from the earth surface that we are recording. So radiation from sun, so when it is incident upon the earth surface, it is either reflected by the surface, it's transmitted into the surface, or it is absorbed and then emitted by the surface. What we see humans is the reflected energy. So remote sensing basically is studying the interaction of this electromagnetic radiation with different land cover objects like land, water, atmosphere, etc. And the basis is that each object reflects different amount of radiation in different wavelength bands based upon its physical, structural and chemical properties, and it forms a unique signature for its identification on remote sensing data. So the term that is used for this is called as spectral signature, which can be understood as a unique spectral response pattern for a particular feature or an object. So the unique spectral response for the three major land cover objects I am discussing here, that is for the vegetation, water and soil. We know the vegetation, the chlorophyll in the leaves, it basically absorbs the red and the blue wavelengths and it reflects the green, and that is why we see the vegetation as green color. And there is very high reflectance in the infrared portion of the spectrum. Water does not reflect infrared at all. The water reflects in the visible range, mainly in the blue and the green region, and we see water blue because of the strong reflectance in this portion of the electromagnetic spectrum, and it will be darker in the higher wavelengths, that is red and the near infrared, where we have no reflectance also. The soil has considerably increasing reflectance throughout the spectrum. It has considerably increasing reflectance throughout the surface. So majority of the radiation that is incident is reflected or absorbed, and little is transmitted. Now why we are capturing in the ranges beyond the ranges that we can see, can be seen with the help of this slide. If I am capturing the picture in A, which is panchromatic range, that is in the visible range of the spectrum 0.4 to 0.7 micrometer, we cannot make a differentiation between the conifer and the deciduous vegetation. Whereas in the infrared portion, the differentiation is possible because of differences in the reflectance. We have higher reflectance for the this and it is able to separate the two features. Similarly, the cloud and the snow, they have high reflectance in the near infrared portion of the spectrum, and it's not easy to separate them. Whereas if we capture the data in the short wave infrared region from 0.1 to 3 micrometer, the low reflectance of snow, it discriminates it from cloud. You can see that cloud is very bright and the snow is dark. So discrimination is possible. That is the reason we are recording in different ranges of electromagnetic spectrum. Now the satellite which is carrying the sensors on board, it is in different orbits. There are two types of orbits in which satellites can be launched: geostationary and sun synchronous. Our remote sensing program is sun synchronous based orbits. Geostationary are mainly used for communication and weather satellites, where the altitude is nearly 36,000 kilometers and period of orbit of the satellite is 24 hours. The sun synchronous satellites, they are normally launched at an altitude varying from 700 kilometers to 1000 kilometers, and the satellite orbit in conjunction with Earth's rotation makes a global coverage of the area possible. So satellite orbital plane is near polar and the altitude is such that the satellite passes each place at the same local sun time. So we have the same illumination geometry that is visible. The sensor on board the satellite has different resolutions which are important. The four resolutions which are important for a sensor are spatial resolution, spectral resolution, radiometric resolution and temporal resolution. Spatial resolution is the ability of the sensor to see fine details, that is the smallest area on the ground from which the energy is recorded is called the spatial resolution, and it is measured in length units, meters. Spectral resolution, in first instance we can call it the number of bands in which the sensor is recording, but actually it is the fineness of the wavelength interval in which the energy is being sensed. Radiometric resolution is the number of quantization levels that a sensor is sensitive, that means how many brightness levels it can record. And temporal resolution is the revisiting capability of the satellite to look at the same location again. So these four parameters are important for a satellite sensor. Coming to Indian Earth Observation Program, India has a very strong Earth observation program varying from its vibrant space segment to strong ground mechanisms for a diversity of applications. There are large number of satellites for land and water applications like ResourceSat-2, ReSat-1. We have high resolution satellites from Cartosat series and ReSat, the microwave satellites. The ocean monitoring is done through OceanSat-2 and Saral. The weather and climate studies are done from INSAT, Kalpana, Megatropics and INSAT 3D satellites. Our imaging capability in terms of spatial resolution varies from as low as 1 kilometer for regional studies, global and regional studies, to 1 meter, that is the cadastral level studies. So we can do meteorological applications like cloud pattern movement, water vapor analysis using the low resolution data, and oceanography studies can be done from 300 to 1100 meter resolution data, and for land views we have a multitude of resolutions available for different applications, and the repeativity that is possible is from 24 days to every 30 minutes repeatability for different satellites. So how the resolution, spatial resolution is important, that we can see from this particular slide. This slide shows how much is the information content that is visible versus the resolution. So we have a scene from Indian Remote Sensing Satellite Ocean Color Monitor, OCM. The small area here which is marked in the box is zoomed here, and we can see that nothing is visible if we look at as our visual interpretation, right? But we can extract meaningful information from by using image processing techniques. As we go towards higher resolution, WIFs, which is 188 meters, to different satellites from LIS 1, LIS 2, LIS 3, and panchromatic data, the information content goes on increasing, that is the fineness of detail goes on increasing, and we can go and see the geometry also of the different objects. The information can be extracted using visual interpretation techniques, using various elements of interpretation, or it can be extracted digitally using various pattern recognition techniques. We can use the most commonly used pattern recognition technique is spectral pattern recognition, which uses the spectral signature of different land cover objects to classify objects into different to classify remote sensing data into different classes or themes. Then the temporal pattern recognition is also possible, where we can use the data for more than one date and extract the temporal information out of the remote sensing data. Our space program has diverse applications. Here we are trying to list very few applications. The application ranges in agriculture, where it is possible for area and productivity estimation, crop yield estimation for 8 major crops. In fisheries, for identification of potential fishing zones, which is also helping our fishermen. It is helpful, our space applications are useful in monitoring the irrigation infrastructure. It is also useful for the groundwater zonation, groundwater prospect zonation and recharge site. It is useful for watershed development and prioritization studies. The space applications are also have examples in natural resource census. There are more examples in forestry, where the assessment of forest cover of the entire country is done on a 2-year cycle. Mapping and monitoring of glaciers and snow cover areas is possible using remote sensing technology. Development of an urban information system using high resolution satellite data on multi-scales ranging from 10,000 to 2,000 is possible using remote sensing data that is available with Indian Remote Sensing Program. Decentralized planning at different panchayat levels, and many applications in weather and climate studies. These applications are disseminated through geospatial services through our web portals. We have a number of web portals for disseminating this useful information. The Bhuvan is a geospatial showcasing Indian imaging capabilities and portraying the thematic information for societal applications. It can be downloaded from Bhuvan and nrc.gov.in. We have India WRIS, a portal for comprehensive data information on India's water resources. We have MOSDAC, which is basically a portal for weather forecasting, cyclone prediction, and continuous weather and ocean data availability. Then we have Biodiversity Information System, which is basically a portal for providing spatial and species data on biodiversity and bioresources. This is our geospatial platform Bhuvan, where it is possible to freely download the Earth observation archive data. Data up to 23 meter resolution is available for free download. And then there are number of services which are available on this platform. We have mapping services, satellite data, thematic services, disaster services, ocean services, create map GIS, base maps. So basically it is a web-based platform for GIS data creation, visualization, geospatial analysis, GIS products and services in participatory GIS environment. There is a strong support towards disaster management by the Indian Space Program. So in association with different nodal agencies, the Decision Support Center is having facilities for flood mapping, for hazard donation, flood inundation mapping, damage assessment and bank erosion studies. In weather and cyclone, intensity and track can be predicted, assessment of the damage that has happened due to the weather and cyclone, alerts for heavy rainfall, and heat wave alerts are also generated using this disaster management studies under space program. Drought monitoring is possible using Indian Space Program. End of season agriculture drought report is brought out and it is carried out by MNCFC. The landslide hazard zonation, damage assessment and rainfall introduced slide forecast has already been demonstrated using our programs. Forest fire mapping, where active forest fire detection and damage assessment is done, and the damage assessment after an earthquake is done. Along with this we have emergency communication support. So the recent studies where the disaster management support was there are two examples which we are citing here, in which the floods in Jammu and Kashmir in 2014 are presented here. So rapid flood mapping was done and monitoring was done almost on daily basis, and cyclone mapping, cyclone tracking and landfall prediction was done. Inundation maps were generated in near real time. So it not only with these studies have demonstrated the potential of Indian Space Program, we have future Earth observation missions which are ranging from high resolution to the land satellites for providing continuity of these applications with our near future missions. We have different series of Cartosat satellites coming up. We have different series of ResourceSat, ReSat, other satellites which are coming up in near future to provide a continuity of these applications and our commitment towards the country's future program. So here with this I would like to quote the quote of our Dr. Vikram Sarabhai, who said that if there are some who question the relevance of space activities in developing nation, if we are to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society. So we hope that with this his vision we continue to provide Indian Space Program to they are not only to Indian continent but also to foreign by launch of various satellites and sensors. Before I end, I would like to thank our Honorable Chairman Dr. A.S. Kiran Kumar, Dr. George Joseph, Dr. Y.V.N. Krishnamurthy, Dr. Senthil Kumar, and Dr. S.K. Srivastav, from whom I have taken the slide support and the guidance to make this presentation. Thank you so much.